Hello everyone. Today we will discuss an example using the OpenSees software. This software is an open source program that can be easily downloaded either for Windows or Mac. Here we can see the Windows version and below the Mac version. We will use this software to give a simple example. So, let's see the example. In Figure 1, we assume a reinforced concrete cross-section. We want to calculate the moment curvature curve for this RC cross-section using the software. We will consider an axial load equal to -200 kN. The yield stress is equal to 500 MPa, the modulus of elasticity is equal to 200 GPa and the hardening ratio equal to 0.1%. For our calculations, we should assume the same material for the confined and the unconfined concrete. Here are the material's parameters. In fact, the stress-strain law of the concrete is given. Here is the main file of our code, so let's go step by step to see all the parameters that we have introduced. The first command is the wipe. It is a command used to remove any existing model. Then, we should create the model using the Model Basic Builder. We assume that we have a two-dimensional model, so the dimension of problem, NDM, is equal to 2 while in each node we have 3 degrees of freedom, NDF. In the next step we have to set some parameters. Initially, the column width and the column depth are introduced. The layers are equal to 10 and are discussed in the next lines of the script. The actual load is assumed equal to -200. The reinforcing steel parameters are the yield stress, the Young's modulus of steel and the steel hardening ratio. Material steel 01 is then defined using the previous values. The uniaxial material concrete 01 is then assumed for concrete. The material tag is equal to 10, while for steel 01 is equal to 20 while the stress-strains law parameters are defined. Then we define the cross-section for nonlinear columns. Firstly, the parameters y1 and z1 are also assumed. The steel bars have diameters of 14 mm or 20 mm. These are the two values for the cross-section of the rebar that we have assumed. Furthermore, we assume that the concrete cover is equal to 3 cm. Two centimeters is the actual cover and 1 centimeter is half of the 20 mm rebar. So, we have introduced all the parameters that concern the model. In the next step, we go to introduce the section. We assume that we have section fiber here. The tag of the section is equal to 1. A rectangular patch, that has a tag equal to 10 is defined. Here we can assume several values if we have different rectangular patches. We use the number of layers for the direction y that we previously defined, while in the z direction we have assumed only one layer. The other values concern the corners of the rectangular. For the steel bars, we assumed that the command is the layer straight. We have assumed different layers in different positions. Specifically, 4 different lines of the cross sections have been assumed. We have assumed one layer here, one layer there, one layer there, and one layer in this direction. In the next step, we must call another TCL file that is named momentcurvature.tcl. It initially needs the number of increments for the analysis and the maximum curvature value. K is the target curvature and the number of increments is the number of analysis increments. So, let's go to the momentcurvature.tcl file. This TCL file can be also downloaded from the manual of the software. Here is an example that uses this TCL file. In fact, we can see an example moment curvature analysis of an RC section. Let's go back to the working file. We will use zero-length section. We should assume 2 nodes in the same position, 0, 0. The node number 1 and the node number 2. In the first node all degrees of freedom are fixed, while in the second node the only fixed is the displacement in y direction. The element's length is equal to 0. The most significant part of the output is the recorder. Specifically, we use the node recorder. There are several recorders about the elements, the nodes, etc. Here the file output is textual. The displacement of the third degree of freedom of node 2 is saved in the recorder file. That means that we save the rotation of node 2. The actual load is defined here. We introduce the actual load in node 2. The load is equal to -200 according to the example, while the other two values are equal to 0. We do static analysis. The integrator is of type load control. The constraints and the numberer are plain. The algorithm used is Newton, while we use some tests to achieve the perfect convergence between the previous and the next step. All the other values are default, so you can find several files and examples in the manual of the software. The plane is linear in the second pattern plane. In this pattern, we define the moment equal to 1, so that the result that we will take from the analysis to be equal with the actual moment. The curvature increment is the maximum curvature over the number of increments. Here we perform displacement control, and we use the displacement control integrator. That means that in node 2 in the third degree of freedom we introduce decay and we do the analysis for the number of increments. You can fully calculate the moment curvature of an RC section using the previous steps and the two files. Let's go to solve and hence run the software. We use the command source, and we add the file name rsection.tcl. The software runs the code and saves the recorder. We can open the recorder using Excel or MATLAB. In our case, Excel was used. Finally, we can see the result. By changing the axis, we can see the result, which is the moment curvature curve. Thank you for your attention.